G'day. Thanks, John and Maxine, for organising this. So, for my first act, I would like to play this organ, but I don't know how to play the organ, so I'll move on to something I do know, which is code. Now, this is a very code-heavy presentation. It'll go for a while, so you need to sort of, get focused. I'm talking about asynchronous programming, as John said. And the subtitle to my talk is Embrace the Async. So the subtext of what I'm talking about today is don't try and fight asynchronous programming, embrace it, and go with it. A lot of the time, we invest a lot of energy as JavaScript programmers, as web programmers, trying to hide asynchronicity, trying to get away from it, trying to make it something that it's not. So I'm going to focus today on some of the techniques you can use to deal with asynchronous programming, and I'll look at some of the upcoming things and some of the newer things that are in our world right now. So what I'm going to do, first of all, I'll look at defining it. What is this thing, asynchronous programming? I think we all have a vague idea of what it means. Then I will be looking at how to construct some basic techniques, abstractions, without using fancy tools. It's something that we can make our own tools to deal with this. We don't have to always import some library just to deal with a simple asynchronous task. So we'll look at how we do that. This will be fairly code-heavy. Then I'll look at some of the advanced abstractions that are available, particularly event emitters. This particular one is a node construct, but events are something that everyone's used to dealing with in the browser and everywhere with JavaScript. Streams, quick look at streams, look at promises, and then looking at ES6 generators for async programming, and interleaved with some ranty stuff in between there. And by the way, so I'm Vagg on the interwebs. My last tweet has a link to this presentation. If you have your computers open and you want to follow along, you can grab code snippets, try them out. So if you hop onto Twitter, Vagg, you can get that link. I have a blog, and also I work with the Node firm a lot. We do consulting for some large companies like PayPal and Netflix, doing migrations to Node. We do a lot of training in there as well. So that's me, and that's my alter egos. In the beginning, programming was about computing. Punch cards. It was about these massive machines that would perform computing tasks for us. They were self-contained number crunchers. We gave them a task to do, and they went and did it, and came back to us with the result. I/O, input and output, was late to the game. So initially, computers were just for batch jobs. You do that job and come back to me. I/O was an afterthought, but a logical progression. I/O is not what is not computing. I/O is what computers wait for. And I/O is the bottleneck in the majority of programs. This is something that we tend to mix up in our programs, but it's really a separate thing to what computers are good at. And I/O is usually hidden. We've turned our programming languages into things where I/O is in the same class as every other operation. Excuse my Java, but this is a typical Java program. It'll read a file, and it'll print that file to the console. So pretty straightforward there. But the thing to note here is that interleaved within each of these statements, some of them do I/O, and some of them just do memory operations. But it all looks the same. So you can identify which ones the I/O operations are. There's the opening file, there's printing to the console, there's reading lines from the file, and there's printing to the console. There's even closing the file. These are all I/O operations. Each time we hit one of those, we're having to wait for something else external to our CPU to happen. But when we're a programmer, we don't have to think about that because our languages give us the ability to ignore that as a separate concern. And I think this is a problem, because I/O is expensive. I've got some different numbers up here for access times, the time cost of some different operations, and you can see there's a clear separation between memory operations and I/O operations. Even solid-state drive random reads are 160 times faster than reading something from main memory. Sorry, slower. So every time you do an I/O operation, even if it's a solid-state drive, it is a different class of operation. It is something completely different to just pulling something from memory. So beyond I/O, the user interface introduces new challenges. So we get I/O in the form of a human, and humans are unpredictable. They're extremely high latency. And sequential programming has limits for UIs for humans. We can force a human into a pattern where we have to do an answer, a question-answer sort of thing, and we can do sequential programming that way. But that's not good UI practice. We want the user to have flexibility. And then networked UIs is a perfect storm. So not only do we have UIs, we have the user variability of UIs delivered over high latency networks. And so we're talking about the web here. And then on top of that, you've got browsers. Programming for browsers, I won't get started on that. On the web, nothing is synchronous. Nothing that you do is synchronous except for the occasional compute job. You're reacting all the time. You're responding to external events. You're responding to user events, to network events, and now browser events. Our browsers are now giving us evented APIs, as John said. We're interacting with the DOM, with storage on the browser, with all sorts of things, geolocation APIs. All these things are evented now. We have to react to them. We don't say, OK, do this, and then when you're done, give me a variable back and I'll continue. You have to submit something, or just wait for something, or hope something's going to happen. Nothing is synchronous in the web. JavaScript is the king of event-driven asynchronous programming. It was born in the browser, and it was designed to respond to user events, and it has timers. I'm very proud of this bit of DHTML here. I've even shown you my code because it's so awesome. So timers were pretty awesome. Not only do we have events, but we could actually make asynchronous things happen. And why is JavaScript good at it? JavaScript has first-class functions. Functions are like any other object. We can pass them around easily. We can put them in arrays. We can store them for later. We can ignore them. We can do all sorts of crazy things to functions. It's not in a lot of other languages. Functions and methods are a bit more awkward to use. In JavaScript, we throw them around like anything else. Closures and scope capturing is really handy. When you have a function that has a function inside of it, you have access to the outside scope. So when you are submitting callbacks, you can still access variables that have been in memory previously. I won't explain that much more. I think it'll come out later on. You probably already know. And it's single-threaded. I think this is a benefit rather than a downside of JavaScript. A lot of people have a go at JavaScript for being single-threaded. I think it's a really good way to deal with scaling programs. If you can build a program that can work in a single thread and scale across multiple processes, then you can scale across multiple computers easily as well. So into Node.js, this is where I tend to work mostly now. I don't do as much work in the browser as I used to. But Node takes the philosophy that asynchronous programming works well for performing many complex parallel tasks in the browser. Why not do the same thing on the server? That's what Node does. But it takes it to an extreme, because not only are you being very reactive, but you're causing a lot of these asynchronous operations to happen as well. You don't do as much of that in the browser, but in Node, you are really pushing this whole asynchronous thing to the limits. You can do synchronous I/O in Node. So this is a classic program structure that you'll find in most languages. Read file sync, it's called, and we will print reading data, read the data, capture it in a variable, and then say we've finished. This is not something you should do in JavaScript. The synchronous methods on file systems don't take advantage of what Node really has to offer. This is what you should be doing in Node, and what you have to do with most Node APIs. So we'll print out reading data. Then we will request that the file be read and give it a callback. And then that is put off onto a queue somewhere, and then we'll print out not finished reading data. At some point in the future, we'll get that callback being fired, and we can say finished reading data. So this is the beginning of what asynchronous programming means, because suddenly you can't read things in order, step 1, 2, 3. You have to change your mindset. to think about how these things are happening in the system. In Node, network I/O is performed with non-blocking system calls. So for file system, we don't use non-blocking, we actually use a thread pool in Node. So we've got these worker threads happening that take on board all the file system operations, and they do things off the main thread and then get back to us when things are done. But for networking, we use non-blocking system calls. So there are some system calls on most systems, either select or epoll, they're called, and they're ways of querying the system, saying, do you have anything for me? If not, I'm going to continue with something else. If you've got something for me, I'll take it and pass it on to whoever needs it. So Node has two methods of doing asynchronous work, but the key is that we have the main JavaScript thread, and it doesn't block for I/O. You ask for I/O to happen, but you don't get to wait for it to complete. You have to deal with this asynchronous problem. So in network I/O, we generally have evented I/O, and this is familiar even if you haven't used Node. It's just normal events. I think the on was actually borrowed from jQuery. This is standard event emitter type pattern. So making a web server in Node, you create the server, and then you listen to these events. You don't have to listen to them all. You don't have to listen to any if you don't want. But you can listen to them and perform things when they happen, in whatever order they happen. The most interesting one there is the request event. Whenever a client connects, we get this request event with a request object and a response object, so we can read from the request and we can write to the client. So that's networked I/O. The callback. JavaScript embraces what is called the continuation passing style. And this is not new. This has been around for a long time, and you can do it in most languages in some form. But JavaScript does it really well. Continuation passing means that when you're executing a program and you submit some operation, you are saying, I want you to continue with this code when you're ready to continue. So classic example is a timer. I've got a set timeout where I'm giving a continuation, which is my pong function or callback. So I'm saying, okay, I'm going to print ping. I want you to set a timer for 100 milliseconds, and I'll give you a continuation to continue with after 100 milliseconds. In Node, we can read a file, it's the same thing. We give a continuation, say continue with execution when you have the file, and here's a callback to continue with. Same with event listeners in the browser. Click handler, that's a continuation as well. When you have an event from the user that's click, we want you to continue with this bit of code. The callback is fundamental in JavaScript. It's the fundamental unit of asynchronous programming. DOM events, browser-based networking, Ajax, WebSockets, server-side events, etc. Node.js I/O operations, Node.js event emitters, streams, even promises, and the async utilities for the ES6 generators. They're all based on callbacks. Callbacks are the fundamental unit that we need to understand. So let's build some basic abstractions. Often, when you hop into some code that is heavily asynchronous, you want to ignore it and turn it into something synchronous, so you'll pull in promises or some other library to make it look understandable. But let's have a look at how we can do this without pulling something else in. So we're going to build a simple program to do an ls, so do a directory listing with Node, and print out the files in descending order of modification time. So it's similar to an ls-ta. Some basic tools, if you're not familiar with Node, we've got fs.readdir, where you give it a directory and you'll get a callback at some point with the list of files or an error. And fs.stat performs a stat system call on a file. We can get modification time, we can find out whether it's a file or a directory or a link. We can do all sorts of stuff with stat, but we really just want the modification time there. So how do we do this? So we've got callbacks here. We're going to go to fs.readdir and give it a callback, and we'll get a file list eventually. When we've got the file list, we're going to just use a normal array for each, because we can safely use ES5 methods in Node. So just a for each of the files, we are going to submit a stat operation, and then we're going to print out the modification time of the file. So what's happening here in Node is you are submitting however many files in the directory you've got, you are submitting that many calls into the system to perform a stat simultaneously. So Node will figure out how many worker threads it can use for this and just queue them up and make them happen. So you don't have to do them one by one. You just throw them all out to the system. The system will figure out when to do them all and give them back to you in some order. The problem is here that we don't have control over the order of returning because stat may be different for files that are on an NFS or on a spinning disk versus a solid-state disk, or for various reasons we have no control over the order that these things come back. So we'll get callbacks coming in different orders. So the result of this program, we'll get the list of files and their modification time, but the order is going to be dependent on the system, and we can't control that. So we need to have some way of collecting them, sorting them, and printing them out. So how do we do that? Let's collect them in a times object. This is a pretty basic way of doing it, but we'll make a times object, and for each file, we will use the file name as the property of the object and store the modification time in there, and then print out that whole object. Unfortunately, each time we get a stat back, we'll get that whole object printed out, so it will actually list out the whole lot in one go. I'm going to try and run this on this computer that's not mine, but we'll see how we go. So we'll run a node REPL, and we'll set the equals for our function, and then I'm going to paste in that code and run it. Now what's happening here is that it's doing an ls. It's doing a file list on the current directory, but each time it's getting this stat callback, it's printing out the whole object. So we start off with the object's got one property, the next time it's got 2, 3, 4, and again we have no control about the order here. The object is being populated in an order that we don't control, and it's just all we know is that we will eventually get all of them on the object. So at the end, the last call there, whichever one was the last one has been put on and printed out. So we have a full object at the end. But what does that mean? What does it mean for it to be the end? Well, we know that because we know how many stat operations we submitted. So here we're going to keep count of callbacks. So we keep a count variable, 0. Each time we get the stat back, we may get an error from the stat because there may be permission issues or something else, but we're just going to print that out and pretend that that's okay. It's not a big deal. We don't have to fail or anything here. We'll just print out an error saying that stat didn't work. We'll store the modification time otherwise, and then we will increment the count. You can see I've got a count incrementer there. And we're going to increment the count and compare it to the number that we're expecting. If they are the same, then we have got the last callback, whichever callback it was. So it could be any one from the number of files. All we want to know is that it was the last one. This is a classic way of doing async in JavaScript. Most of your libraries that do asynchronous operations for you will use callback counting mechanisms. This is underneath most, like it's underneath async.js. It'd be underneath promises. It's underneath a lot of things. So this is a fundamental unit of asynchronous programming. Sorry about the readability here, but I'm trying to fit them on the slide, so I'll probably space things out a bit more. So if we run this, then we only get one, because it was the last one, and so we'll get the full object. So now we've got a trigger for the last one happening, and we've got a full object of modification times. We can continue on with the rest of the logic, which is sorting them. So that's a simple sort, array sort there. That's just comparing modification times. Once the array is sorted, we'll print out the whole list separated by a new line. So all we want is the file list. So that's an asynchronous program in JavaScript with no helper libraries that prints out things ordered in the right way. And if we say, let's touch index.html and run it again, you can see index.html comes at the top there. So we've done our job with no helper libraries using simple callback counting. It's not the prettiest, and we're starting to get into territory that people often call callback hell, or the pyramid of doom, because it's, the pyramid is going that way. But that's not really a big deal, because you can just rearrange things. Functions can be named and pulled out. And we're using scope here as well. So the outer scope, which is the callback to readdir, has our list of files, and that's available to every one of the functions within here. And down the bottom there, we're using, again, in the file list for each, the file object is being used inside an inner callback. So this closure here accesses this file object. So we're using scope capturing here to take advantage of it, but we can flatten this pyramid of doom and do away with that bogus argument for asynchronous. So let's extract a utility from it. This is a really simple utility to count callbacks and trigger something when it's done. I've called it counter. All it does is, the usage down here, we call counter with a number and give it a callback function. It gives us a new function, which we can call as many times as we want. As soon as we've called it this number of times, it will call this callback. So let's just quickly run that because it's fairly simple. We've got counter in the system. Now we've got so the done is now a function. So we can call done, doesn't do anything. 1, 2, 3, 4, and it gets the callback. So it's just simple callback counting here utility, and we can replace the code in our a little function with the count function. So up the top there, we create a new function called done, and we call done every time we get a stat. And once it's done that many times, it will call sort and print, which will do the work for us of sorting and printing. So there's a handy little utility. This is the same thing with error handling, because sometimes we can care about errors. So in this case, what this particular one is doing is on the first error, in Node-style callbacks, the error argument is always first on the callback. It's either an error object or null. So if we get an error object, we're going to say we're done. We'll call the callback with the error and not continue counting on anymore. We can't stop the asynchronous operations from happening, but we won't pass them on to the callee. There's a great utility called after that's available that you can use in the browser or in Node that does exactly this. It's got a little bit more flexibility around how you handle errors too. So moving on, let's build something a bit more interesting. This one's an asynchronous map. So map in ES5 is really fun. You can take an array, give it a callback, and the callback will mutate each element of the array. And once you return that, you are saying, this is what I want it to turn into. So in this case, we're turning an array of 3 elements. We're multiplying each element by 10, and we will get back a new array, which is 10 times each element. That's really nice. I like using array map, but it's no good for asynchronous operations because there's no sense of asynchronicity here. You can't say, hang on, I've got to go and read something from the file system before I get back to you. You have to get back now. It wants a return value. So we want something that can take callbacks. So this is a bit much for one screen, but anyway, this is an asynchronous map operation. It's a function that takes three arguments. First one is an array. The second argument is a work callback, which is a callback that we want to mutate our elements. And this function, we expect to be asynchronous, so we're going to give it a callback when we use it, each time we use it, and then we'll get a value back. So, and then the callback at the end there is what we want to call when we're done with everything. So we're going to keep track of everything with this result array. We're going to use our counter function again because we know how many elements we're going to collect. And this time we've got error handling as well. Once we've collected all the elements, because again they may happen in any order, we don't have a control over which element of the array is touched first. And then we're going to use ES5's array for each, taking advantage of the fact that the second argument is the index of the array. We'll call the work callback function with the element. We will get a result or an error. We'll stick that result in the right index of our results. So again, the result array is going to be populated in some random order that we don't control. All we know is when we've got everything, and done will be called, and then we'll be able to call the original callback with the full result. And again, there's a utility called map async that I like to use for this kind of pattern. So you don't have to write these things yourself, but they're not that hard to understand. This is it in practice, just using a normal synchronous type operation, which is what I showed you in the first one. We want to take an array of 3 things, multiply them all by 10, and print them out to the console. The bottom code there is the exact same form as the top code, sorry, exact same procedure as the top code, except we're using our little utility. There's no need for asynchronous here, but we're still using the callback. But we can stick it into our file listing application. So down the bottom, we are saying async map, the list of files, what we want to do for each file, and then what we want to do when we've got all the results. We changed it a little bit because stat file now returns this more complex object that has both the file and the modification time. And the reason we do that is because we're going to have difficulty capturing the file name in our scope like we did previously, so we want to capture it in some other way. So at the end, we'll end up with an array full of these objects, which we'll get here, or perhaps an error. I haven't done anything with the error in this case, but we're going to presume we're going to get that. We'll sort them and then print them out again. So this works exactly like the previous one, except it uses our nice little array async map utility. And the nice side effect here is that we've done away with all explicit state. We're not storing state anywhere here. We're not storing counters or objects or arrays to collect things in. This has become a very functional program. So we submit these functions to do all this work and expect them to come back in the end. And because we're taking care of errors, we can be assured that we will get something back, even if it's an error. So asynchronous is one thing. Doing lots of things at the same time is fine, but sometimes you want to do one thing at a time. So in this example, we're going to build a program that's just like cat in most Unixes. So we want to cat multiple files into a single file, and we expect them to be done in order. So, for example, I've got, hang on. I've got 3 files here called cat file, and each of them is 5 words from my dictionary starting each letter. So cat file 1 has the A's, etc. So we know what order they're in. So when we do a cat file, all of them, and we direct it to a file called cat, we expect them to be in the right order. Okay, that's fair enough. In Node, we're going to have problems with that because the ordering is going to be an issue. But so the tools we're going to use read file to read the contents of a file, and then we're going to use append file to append some data to an existing file or make a new file if it doesn't exist. So this is a naive approach. Given an array of files, submit read file operations for them, and when we get each one back, append that contents to the file that we care about. So this is just sending out, if we've got 4 files, we're going to send out 4 read file operations. They will happen in their own time, all come back in their own order, and we'll chuck them into the file that we, the output file we care about. So we'll see a problem here though, which is probably obvious. So files. Okay, so we've got the list of files in an array down there, and we've got what we want to output it to. If we paste in the code, nope, that's not the code. This is the code. So we're pasting in that code that we had on the screen. It happens. It doesn't tell us it's finished because they're just all happening together. And if we look at the file cat, in this case they've done it in order. If I do it again, I'll do it a few times because no, it's doing it in order again. It's not playing as nicely as I'd like it to. Command V. Okay, well, it's playing nicely at the moment, but it doesn't have to play nicely. In this case, we've got 4 files. They're all about the same size, so it takes the operating system about the same time to read them and give us the contents. And because we've got these worker threads, we've got 4 worker threads, it's just conveniently happening that we're getting them back in order. But they may not come back in the order that we expect. You understand anyway. So this is happening nicely by chance, but there's nothing to say that it won't happen in the right order. So we're going to make sure it's ordered by using a sequential operation. We want to read each file one by one. So read a file, put it to the output, read another file, put it to the output. This is what the cat command actually does. So how do we do that in an asynchronous environment? So I've extracted out the cat file functionality. That's just for a single file. And I've got this little construct down the bottom here that is a named function called next. And it takes an index, which is the index of the files array. For each file, it will run cat file. And then once cat file is done and calls its callback, we're going to call the function again with the next index. So it's a recursive asynchronous function. And to start it all off, down the bottom there, we're going to call next with 0. You can also call this as an immediately invoked function expression where you put brackets around it and just call it with 0, but it's a little bit more obscure to read that way. So this next function is happening recursively, but it's happening across ticks of the event loop. So it could be quite a while before it's ready to call again, but it will call itself until we've got enough entries. So we know how many entries we want, and we'll stop there. So so run that. We can actually get feedback now because we know when it's done. The last one has happened. So that's all good. And that will always put them in the right order. So that's a handy little utility there for doing sequential operations. Just have a function that calls itself again with the next one. It's really not that hard. And you can actually, it's easy to extract that into a utility. You might call it serial or series. And you'll find something like that in most asynchronous helper libraries like async.js. I think it's for each series or just series. So, but it's really not a hard construct to build. Some advanced abstractions: event emitter, streams, and promises. We'll have a quick look at each of these. Event emitters in Node, as I said, are like most other environments. jQuery's got its own event emitters. So sometimes a callback is not enough. You want something to be called multiple times. In Node, it's a general practice that you should only call a callback once from an API. So if you need to call a callback more than once, use an event emitter for it. If you've got multiple types of responses, use an event emitter. So if you, like, when we read a file, we've got a response that's going to come back with either an error or the data. That's all. There's nothing else that's going to happen. If you've got multiple different things that are going to happen, then you'll want to use an event emitter. If you want to communicate complex state, you can use an event emitter. So sometimes something will mutate over time. An event emitter is a really good way to communicate that to a user of your API. Event emitter in Node is really easy. Just make a new event emitter object. You've got on and emit. You can do the normal things, remove listener, remove all listeners, etc. There's only one surprise. It's really a simple function. The only surprise is the error event. If you emit an error event and there's nothing listening to the error event, then it will throw an uncaught exception, which, in my opinion, is a good thing because You want errors to either make your program die so that you have to fix them, or you want to be forced to handle these things. You don't want errors to disappear into nowhere. You need to handle errors. In the Node core API, we've got, as I showed before, the networking is all event emitters. In this case, the server. When you call HTTP create server, it's creating an event emitter and sending it back to you, and it'll emit these events over time while the server is active. And even when it's inactive, it'll give you shutting down events. So moving on to streams. Streams, what are they for? They're for chunked I/O handling or chunked data processing. So streams are an abstraction that's suited to flowing data. It's like plumbing. So you want to pipe streams together. You want to have streams that flow one way or the other way or both ways. The analogies are all about plumbing. Streams are good for processing very large amounts of data with minimal memory. You can process blobs of data that are bigger than the amount of memory you've got on a computer with very little memory with streams, because you're only dealing with small bits at a time. Processes, if you want to process many asynchronous streams at the same time, streams are good for that too, because you can set lots of things in motion, lots of streams in motion, and your system will only deal with what it can, what the CPU and what the memory can deal with at that time. So they're a good way to make multiple things happen. And this is how Node scales with HTTP particularly. You can throw lots of streams around and you can have millions of connections to a single process, and it's only doing what it can. It's only dealing with the amount of data that it can at a time. So they're also a good way of pushing data out before your processing is completed. So normally you'll be doing some rendering of a template or something, and you have to wait till everything's done and then you give it to the client. With streams, you can connect your processing to the output from the input and be pushing stuff out to the client or the receiver before you've finished your input. So if you have priority of getting first byte to the client as soon as possible, then you would use Node streams or some other streaming abstraction to get things out as quickly as possible. And back pressure, an important concept. I hope Damon's going to explain that later on when he talks about streams. Back pressure is a way of signaling to the source of data that you can't consume it fast enough, so you need to slow down. It's built into TCP. It's built into most operating systems. This concept of hold up, I can't deal with this data. You need to wait. So when you're sucking things off the web, your computer is sending the signal back to the server. I can only receive it at this rate, so don't give it to me too fast. Streams have those built in, if they're good streams, where you can signal this back pressure, so you don't just have big buffering of memory. I'm not going to run this. It's a contrived example, but we're taking, what have we got there, 6 different types of streams and piping them together. So at the top there we've got a request stream, which is just doing an HTTP GET from this URL, which is from the NPM registry. It's a 35 megabyte, currently anyway, it's probably grown since the time I measured it. It's a 35 megabyte JSON document, not nicely formatted, it's just a big blob of JSON, and it's got all of the packages currently in NPM. And it's an array of objects in JSON. So normally what you might, if you wanted to look at that, you'd probably download it all and then do a JSON parse of some kind and then blow up your memory because it's too big. What we're going to do here, though, is going to stream it out from the server, and as soon as we get something useful, we're going to stick it through to a streaming JSON parser. So what that does is it's going to look at the contents. It knows it's an array. We're telling it it's an array. As soon as it finds an object in that array, it's going to spit it out to the next stream. The next stream knows it's going to get objects rather than binary data or strings, and it knows the rough form. And if each object that it gets, we've actually made a custom processor here. If the object that it gets has a name property and a description property, because sometimes the registry doesn't have complete documents in it, so we're going to do some sanity checking there, we will push it on to the next stream. This is a utility node for building really simple duplex streams. In this case, all we're going to push on is a new object. We're going to convert the original objects into this really simple object with 2 properties, a name and a description. The next stream is a CSV parser, writer, with a name and a description. So we're saying print out, for each object you get, print out a string that's only got 2 columns. The next one is a gzip stream, which is going to gzip the data as it comes through. And the last one is a writable stream to the file system. So when we plug this all together, set it in motion, as soon as we get data from the server, we're going to pass it through the chain and start writing compressed CSV name and description version of the NPM registry. So very efficient. It'll start working as soon as it's got data to work with. And it's a great way of dealing with asynchronous operations. And you can do many of these in the system at the same time, and it will just do what it can, and back pressure will sort it all out. Promises. I don't want to dwell on promises too much because I'm pretty sure that a lot of you are familiar with them. Promises are an abstraction with a very well-defined API. And that's the beauty of promises for most people, is that the API is very tight. The current spec is called Promises A+, and you can find details at that page. If you're using promises, I'd recommend you go and read that to understand what you're dealing with. Simply put, a promise is an object with a then method which is a hook into the state and data represented by that promise. The promise has 3 states: pending, fulfilled, and rejected. Very well-defined transitions between those states, and this is the interface you'd use. Promise.then, 2 callbacks, both are optional. Either you get a fulfilled or a rejected. And they're composable. You can put them together, you can return promises from within the then callback. You can do all sorts of things to make these things, give them complex flow. Our original example, using a promise library in Node called Q. There's a bunch of them available. I'm pretty sure Q is Promises A+ compliant. This is our read directory. What we're doing down the bottom here is converting each of our files into a promise using just array map. So this here creates a new promise for each file, and each of those promises is an asynchronous operation to do a stat. Once they're all done, we can do the sort and print. So that's another way of doing what we did earlier. But what's the catch with promises? There is a catch. They're not free. Error handling is a second-class citizen in promises, in my opinion. There's no error handling in here. If something goes wrong, the error is caught and suspended in state somewhere and not dealt with. You're not forced to deal with the error. You don't get any uncaught exceptions. Even if there's a programmer error, like you've typed a variable name wrong, promises will catch them for you and keep them and not let you know unless you start registering a failed listener. So, in my opinion, promises have got a problem with error handling because you don't have to use error handling. You don't have to do these things. You can just throw them out and off you go. They're a heavyweight abstraction. For simple tasks, they're a very heavy covering on something that should be simple, and they can easily mask problems, particularly performance problems, because it's not always intuitive what order things are happening, whether they're sequential, whether they're parallel. And they're also viral. They infect everything they touch. You need clear barriers of when you're using promises and when you're not. Otherwise, everything has to be promisey in some way. But your mileage may vary with these. I know they're very popular in browsers, in front-end application programming. Not as popular in server-side because we're dealing with so much asynchronicity that we need higher visibility into what's going on. But again, I'm not going to criticize people for using promises. I just think that there are some issues. Just quickly, I'm going to look at ES6 generators. I haven't really got much time to look at this. I'm running out of time now. But generators are often sold as some sort of magic to solve asynchronous pain. That once we get ES6, we're going to do away with asynchronous programming and everything's going to look sequential. Are they magic? No, they're not actually magic. And they're not actually an asynchronous programming construct. They're simply a protocol, so it's a well-defined protocol, a bit like promises, but with additional syntactic sugar. So ES6 gives us these new generator functions. So function star defines this thing, it returns a generator. And in our generator, we have this yield. So a generator is simply a function that can return multiple times. So it's like having multiple return statements. Not only that, but you can communicate back with the generator. So it's two-way communication. Quite nifty. Just quickly, we've got an example here. This is a pseudo-random number generator. It's a linear congruential pseudo-random number generator. It's just a simple example of something that needs to emit data multiple times. In this case, I'm only doing 10, so we seed it with some number. The same seed will give us the same sequence of numbers, so you want a good seed for a random number generator. And we'll print out 10 random numbers. So that's nothing to do with generators, that's just a random number generator. But we'll turn it into a generator. So this is a pseudo-random number generator. Using function star. And we've got a while true here, so we're just going to continue on and on and on. But each time, we're going to yield. So what's happening here is, each time through the loop, we're saying, return this value. So it's like having a return in there, but we get to come back to it. But we don't have to come back to it. So it's not like a spinning thing off in your process. And you'd use it like this. Calling a generator function, we call it with a seed here, will return us a generator. And that doesn't do anything initially. It's an object that has a next function on it. Whenever we call next, it executes the function until we get to a yield. So when we get to a yield, we get back an object with a value property. So each one of those lines is going to print out a new random number. At the end, it's not going to do any more. That thing could be garbage collected and it would disappear, even though it's got a while true in it. But it doesn't have to be, that exact form there doesn't have to be, you don't have to wait for ES6 for this, because the protocol is simply something that you could implement in Internet Explorer 6. This is the same code. I could run this same function, this same batch of code down the bottom here with this ES3 function. So when we call random, we're going to return an object that has a next function. That next function, whenever you call it, will return a new object that's got a value. It's also got a done property, and in this case, it's never done, so it's always going to be false. So generators can also, you can feed back into them. In this case here, we're going to reseed the random number generator, so we're seeding it with 10. After 4 values, we're going to seed it with 3 values. We're going to seed it back with 10 again. And you can see at the top there, yield, in this case, may return a value. So when we've returned 10, it's going to feed it back in, and we can reseed it. So that will start the sequence again. So generators are two-way communication. But so far, nothing about asynchronous programming. For asynchronous programming, this is a technique that people are starting to use generators for. We invert the use of them. So instead of consuming from generators, we write our code in a generator and get some external helper library to help us with asynchronous programming. In this, we're making a simple timer that's just a random timeout after some up to 1 second. And we've got a sequential job here where we want to say, for some up to 1 second, we want to do some work. When that work is done, get back to us with a value, print it out to the console. So this function is going to suspend 3 times and submit this timer function to something else, which will run it and return the result of it. So the timer function itself will take up to 3 seconds to execute, but it looks sequential. And this is why a lot of people are attracted to generators for asynchronous programming, because the desire is to get back to sequential programming. To run it, just something like this would work, where we give a generator function to this function. It creates the generator, and then it calls this sequential programming thing again. We've got this next function that we're going to recursively call. Each time we call the next function, we're going to get the generator next, and we're going to assume that the value of the yield is a function that we can call, which is an asynchronous function that has this common callback pattern. So we're going to make assumptions here that the function that the generator is yielding is of a particular pattern. Once we have got the return value of that asynchronous function, we're going to loop again and pass the result back into the generator, which will be the return of the yield. If you're interested in this pattern, you can use it in Node version 11 with the Harmony flag. I recommend having a look at TJ Holloway-Chuck's Co library. It does this and a lot of other clever things as well. And the extension to this is because the assumption here is that we are dealing with functions that only take a callback. So we need to convert all of our asynchronous work into that pattern. And in this, we're simulating that because we want to have a timer of a set value. So instead of, you can't just say timer, yield a timer, and with these arguments, we want to make a new callback that takes only a callback argument. So this is the sort of pattern we'd use to create a new function that would work with our little runner. So in this way, you can do multiple types of, many different types of asynchronous work just by converting each of those functions into this pattern. So what's the catch? It's not widely available, obviously. Again, Node, if you want to use it in Node, you've got to use Node, the development version, the unstable version, with a special flag. It's not well optimized yet, so it's fairly new in V8, for example. It's probably been in SpiderMonkey for a long time, so it's probably a bit better there. It's got some optimization work to go, so it's still a little bit slower. And it's serial execution by default. This pattern is serial execution, so you're expecting one thing after the other. And as soon as you start to force things into this serial-style programming, you run the risk of not taking advantage of an asynchronous system. So to do parallel operations requires some extra steps, not as obvious, so you're not as prompted to do things in an optimal way. And just an open question, is it intuitive? You look at that code without explanation, do you know what that's doing? I just have concerns about readability here. But perhaps everyone's going to be doing this in the future, so it won't be a concern. So that's it, asynchronous programming. My argument is to accept it. It's the new norm. It's how the browser works. It's how the world works. It's how every system should work, except for number crunching systems. If you're in academia and you're doing number crunching, fine. Go and do that in C, and cool. But in the real world, we're dealing with asynchronous systems. And the more we try to munge things into synchronicity, into serial flows where we can read things from one step to the next, we are not taking advantage of the optimizations available. And we're getting ourselves into knots, and we're covering up the real world. So my message to you is take this away and embrace asynchronicity. Stop trying to cover it up with abstractions. Just accept that's how things are. Start to think that way. And that's it from me.